Thank you everyone for being here. Some of you know me already. I am Alfredo. I'm a postdoc now in Oxford, but I was a postdoc for 2 years here at Imperial in the civil and environmental engineering department. And I'm working mostly now on environmental assisted cracking. More specifically on hydrogen and embrittlement. Well, maybe some of you are not familiar with this term, but I know at the end of the talk you will know a little bit more about it. So I've entitled this work or this presentation today. Well, it's a long title actually, so we could summarize it by hydrogen-resistant metals to reshape the energy landscape. So we'll be doing a, let's say, overview about the hydrogen embrittlement problem, how it affects us, how it affects metals, and we will talk a bit on how we can study it and solve it. So just a little bit about me, although already many of you know me. I did my PhD in Spain. I finished in 2021 when I received an offer to come to Imperial as a postdoc. So I moved to London and I stayed here until 2023 when my whole group moved to Oxford, so I moved with them. And now we are happily settled there, although we are setting up the lab slowly. As you can see, some of the people in the picture are here. But well, we are a massive group now, like 25 people, including class PhD students, master students, and so on. And now I'm here with you, giving you this talk. So this is what we have in Oxford. We are based in the, I'm not sure if you've been there, but we are based in the Yankee building in the engineering science department. This is how the lab looks now. At the beginning, it was just an empty space. Emilio is our PI, so he's the head of the group. And we have right now 2 experimental postdocs, apart from me, and a postdoc working in the lab, though we expect in the upcoming months we'll have out of the PhD students and other postdocs. And our lab is called Hydrogen Embrittlement and SCC Lab because we mainly work on environmental assisted cracking and characterizing these 2 phenomena. And we can do a bunch of stuff that includes electrochemical charging and any kind in general of electrochemical experiment, let's say for example corrosion. We can do permeation of hydrogen through membranes using both electrochemical methods and gaseous permeation. We can do thermal distortion spectroscopy to detect tiny amounts of hydrogen, and we can do also mechanical testing. Of course, in aggressive environments. So today, I'm going to lead you through a series of topics, particularly through a series of let's say three areas of research that we are dealing with right now in the lab. So all of the results that I will show today are pretty fresh. Some of them are published, and some of them are not. And finally, we will say a few concluding remarks, so you try to remember as much as you can from the presentation. And I would like to thank all my collaborators, which are not few, from here in the UK, from Spain, and from other countries. And also special thanks to Sancho and Claudia that are here, that are unofficially 2 of my PhD students, and also friends. So. Okay, maybe if you read the title, the first thing you wanted is why hydrogen. Okay, so maybe all of you know right now that we need to replace all the traditional fossil fuel sources by something cleaner that let's say it's less hazardous for the environment, and hydrogen is becoming one of the main alternatives here. Because it's really abundant. It's actually it's the most abundant element on the universe. And then if it's produced from green electricity, it's completely clean. The only waste products are water vapor, or the only waste product is water vapor. So what's really the future of hydrogen energy? Because many people are talking about hydrogen to power cars, to power trucks, to heat our boilers. But the real future of hydrogen is that it's a perfect energy vector. So basically, you can take the surplus of the renewable energy sources, so the electricity that we are not consuming at that time, and we can use that electricity instead of wasting it. We can use it to produce hydrogen gas, and just through water electrolysis, and that hydrogen gas can be stored easily, unlike electricity, where we need massive batteries to store electricity. So hydrogen can be stored and can be transported to a final use. Okay, and actually, the fact that hydrogen is considered the perfect energy vector is boosting its demand in the upcoming years. And actually, it's thought that by 2050, around 20 or between 20 and 35 of UK's final energy consumption will come from hydrogen sources. But the main question that we have to arise here is, do we really have a reliable infrastructure to deal with huge volumes of hydrogen to meet these hydrogen demands? And this is where my work starts, because we are going to talk about something that's called hydrogen embrittlement, that's related to those materials that will be handling such hydrogen pressures or such hydrogen volumes. So there is an issue related to hydrogen materials compatibility that's called hydrogen embrittlement, and it's a process. Some people consider it some kind of corrosion process, but then we will see exactly what it is. That provokes mainly a degradation of the mechanical property in metals. I'm going to focus on metals. My work is focused on hydrogen and metals interactions, although hydrogen can also, let's say, modify the properties of polymers and basically another material that's in contact with. And this degradation of mechanical properties in metals is going to provoke a failure or a premature failure of any structure or component that's in contact with the hydrogen. But hydrogen is a very particular phenomenon, and it only happens if there are three conditions that happen at the same time. So you of course need to have a hydrogen-rich environment, which can be, now we are talking about hydrogen gas, but it could be, for example, any kind of corrosion process is going to produce hydrogen as well. Okay, so for example, if you have an offshore structure that's being corroded in the middle of the ocean, then you can have also hydrogen uptake from the water. Or it can happen during welding, or I don't know, transport of an acid, like in a vessel, or whatever situation that you can imagine where we have hydrogen. Actually, even from the moisture of the air, we can have hydrogen uptake. So we need a hydrogen-rich environment. We need mechanical loads. Okay, cracking due to hydrogen embrittlement only can happen if you have a load, if you have a stress in your material. That doesn't need to be really direct, so it can even be a residual stress, okay, from a sample from the manufacturing process. And we need to have a susceptible metal. So not all of the metals are susceptible to hydrogen embrittlement. Usually, the stronger a metal is, so the higher its strength, then the more susceptible it's going to be to hydrogen embrittlement. Okay, so usually carbon steels, the ones that we typically see in buildings for construction that have low yield stress, like around 300, they are not going to be very susceptible to hydrogen embrittlement unless we have an environment that can introduce a lot of hydrogen or very specific conditions. But what's clear is that this is a problem that can provoke the premature failure of structures, as you can see examples there. And usually it's a failure that happens very fast, so it's brittle and cracking takes place really fast. So we need to address it to make sure that that we don't have this kind of failure in components. And what it looks like, so this slide is, I just want to show which are the consequences of hydrogen embrittlement when you see the strength of a metal or the stress-strain behavior of a metal. In this case, for Inconel 718, Claudia is familiar here probably. It's just an example for a nickel-based alloy that's typically used to manufacture aerospace components. where you have it's not exactly hydrogen embrittlement, but there is hydrogen involved, and hydrogen embrittlement can take place. So it's important to study hydrogen embrittlement in this kind of alloys. And what happens when we have hydrogen is, if this is our standard response, we have hydrogen in the metal, like this is the stress in the strain, and what hydrogen is doing, so this would be the example of the red curve, is as the name says, exactly, it's a great loss of ductility in your material. Okay, and this is translated in a very brittle behavior. So you can compare here two samples that were tested without hydrogen and with hydrogen. In the upper one, you can see some kind of like ductile behavior, so some reduction in area of your sample before fracture, while in the hydrogen one, the fracture is completely brittle, and actually you can see this intergranular fracture that's typical of this kind of failures due to hydrogen embrittlement. So this is what hydrogen does to your material. This is of course an example that we obtain in the lab, okay, not like in a real like in situ component, but it's just for you to see which are the consequences of hydrogen on the mechanical performance. So actually what really happens with hydrogen is that it can be absorbed from a hydrogen-rich environment. As I said before, it can be whatever. Let's focus on hydrogen gas, okay? One, it is absorbed, like, I hope we can see it again. One, it is absorbed. Hydrogen is so tiny that it can diffuse very easily in the lattice of your metal, okay, through the interstitial lattice sites, and it can get trapped in defects during this lattice diffusion. And what's going to happen, like defects that can be grain boundaries, any other internal interface, inclusions, carbides, dislocations, pores, cracks. So hydrogen, during that diffusion, it's going to be accumulated there. And when in those defects you reach, let's say, a critical hydrogen concentration, and you have a load, remember, that's important, then that's going to provoke cracking. Okay, so that cracking is going to happen before than if you didn't have any hydrogen in your material. Okay, so that's like the process of hydrogen embrittlement. And you can imagine that then, given that usually cracks start in these defects that tend to accumulate hydrogen, it's very important to characterize them. So these are called usually hydrogen traps. Okay, and there are many methods to characterize how these defects can capture hydrogen, but a very, let's say, famous one, or like the most interesting one right now, it's atom probe tomography, that many of you may be aware of. In atom probe, hydrogen is so actually small and light that we cannot detect it, but we can detect deuterium that has the same behavior as hydrogen inside the material, okay, because it's an isotope of hydrogen. And then, okay, that's the process of how this hydrogen is traveling through your material, getting trapped in those small defects and provoking damage. But then, what we also study in our group is, okay, once you have hydrogen in those defects, out of hydrogen, how it is like physically, fundamentally, like making that damage in your material, okay? So which is the model of damage. And there are different models that try to, or have tried during the last decades, like hydrogen embrittlement was discovered around, like in the late 19th century. There are different models that have tried to explain how hydrogen makes this damage in your material. There are two that are the most accepted ones and the most important ones, which are HEVI and HELP. I know the names are funny. HEVI means hydrogen enhanced decohesion, and HELP means hydrogen enhanced localized plasticity. So this is the easiest to understand. So they say that hydrogen, once it's in your, let's say, network, in your material, in your lattice, is able to reduce the interatomic energy between your metallic atoms. Okay? So then when you pull, and imagine you have hydrogen between your grain boundaries, the energy that you need to split those grain boundaries is lower than if you didn't have hydrogen. Okay? So that's why one of the main manifestations of hydrogen, once you have a broken sample in the lab, is this kind of intergranular fracture. So that's the first theory. But some people say that that's not enough to explain why hydrogen embrittlement takes place in many of the cases, and that there must be something else that's going on in the material. And then the second theory arises, that's this hydrogen-enhanced localized plasticity. And it basically says that hydrogen is able to interact with these locations during plasticity, or during plastic deformation, and actually reduce the energy that is needed for this location mobility. So it's not as simple as this. I'm trying to put it very simple and straightforward so you more or less understand. There are a lot of things behind it, but it's basically that. So in the end, what happens, according to this theory, is that you have hydrogen that is enhancing your dislocation mobility. So you have localized plasticity around your crack, and that's going to provoke this final, like, let's say, more premature failure. Okay? Then some other researchers say that these two mechanisms need to happen at the same time, or that one needs to mediate the other, so there needs to be synergy between both for them to really provoke this damage in your material. So basically, they say that these locations may be helping hydrogen move to those defects, where then you have some kind of decohesion. Okay, so we have two mechanisms that then can work together in very complex ways. These locations and plasticity are there playing their role, and we are studying those phenomena. Okay. And actually, I'm not making all this up. I want to show you that this is a real issue for us. So it's actually a roadmap for UK. If you just type hydrogen UK government, you have all the plans that the government has regarding hydrogen. But if you go also to the webpage of the Henry Royce Institute, that is the UK National Institute for Advanced Research, Materials and Innovation, Research and Innovation, they have several roadmaps of the things that they believe are more important to study regarding materials in the UK. And there is one that is directly materials for end-to-end hydrogen. So basically what I'm doing, so studying materials that can be used to work directly in contact with hydrogen. And then there are others that are also related, because we have materials for energy transition, materials for low carbon production of hydrogen, blah, blah. Degradation of materials for net zero, materials for fusion. So there are really a lot of applications where hydrogen is going to be involved. For example, in fusion, if you have, as I said, hydrogen isotopes involved, then you can have hydrogen embrittlement and things like that. So it's something that's really relevant nowadays, and even more from the funding point of view. So that's something that the researchers also like a lot, to write proposals based on that. And hydrogen embrittlement, even though I have put it to you in a very simplified way, it has a lot of key areas, in the same, let's say, topic. So actually, even though you say hydrogen embrittlement is a very specific topic, maybe for you that are not familiar with it, for me it's very broad. I can say, okay, but I'm an expert on this thing regarding hydrogen embrittlement. So we have the materials characterization side. Here, some of us are more familiar with that side, because of course, to understand how hydrogen is moving and interacting with your defects, you need to understand your material, right? Then we have everything related to hydrogen exposure. How can hydrogen be absorbed from any different media that we have around, let's say, our structure? Then we have the side of mechanical testing. Okay, I have samples with hydrogen, samples with no hydrogen. I need to test what's the difference of behavior between them. This includes fatigue, fracture, typical tensile tests, etc. Then studying all these fundamental mechanisms on how hydrogen damages my material. That's the slide that I showed you with the different mechanisms. Then we have prevention and mitigation. So which strategies can we adopt to prevent this phenomena? Can we use paintings to avoid hydrogen uptake? Can we use something else? Which materials, which should be the strength of my material so I prevent hydrogen? Which kind of microstructure? Bigger grains, smaller grains? What can we do? So that's another topic. And then modeling and simulation. Okay. Originally, my group was like expert in modeling and simulation of hydrogen embrittlement problems, and I was the first experimentalist in the group. So I brought some of the areas to the group. And today we are going to talk particularly about this part. This is something we are also like working on, but it's, let's say, we are starting, so I couldn't bring like something like very solid for you. So we are going to focus on those four. And what I'm going to do, as I said before, is I'm going to comment, and I'll try to be somehow fast, three, let's say, of these areas. So 3 cases that we have been working on in the lab, okay? So one of them is measuring hydrogen diffusion, because if you remember, as I saw in the animation, as I showed in the animation, is hydrogen is diffusing like through my material until it encounters defects and it gets trapped there, okay? So that diffusivity, it's very important, and it's going to determine if a material is going to be more embrittle or less embrittle by hydrogen. Okay, so it's really important to characterize it. So actually you can see that this hydrogen diffusivity can be directly related to the crack growth rate in metals, or in some of the metals. So it's really like a parameter that we really need to know, okay, to do a proper design of the structure when it's going to work in hydrogen. And there are two main ways to characterize hydrogen diffusion in the lab. And we can do all of them, actually more than this. One of them is electropermeation, so it involves electrochemistry. And the other one is distortion spectroscopy, so it involves like some kind of mass spec measurements. Okay? And we found that there is not a really like direct comparison in the literature to see which is the technique that provides a more accurate or more reliable result. Okay? Most of the people rely on electropermeation because it's the one that's most straightforward, but it has its limitations. So the aim of this paper was to compare those techniques from a statistical point of view. So performing loads of experiments for each technique and comparing which one could provide the, let's say, more accurate results. So the first method is hydrogen permeation. I'll just put it very simple. We have 2 electrochemical cells. The cell we produce hydrogen, the cell on the right-hand side where we detect hydrogen. Our sample in the middle. In this case, we wanted to study iron. We just took iron because we just wanted to compare the methods. So we have an iron sample with a certain thickness, and we produce hydrogen on one side. Then you have a difference of concentration, a gradient of concentration. So hydrogen is going to try to diffuse to the other side, okay, where I can detect it. What do I measure? I measure the time that it takes for hydrogen to get to the other side. So I start producing hydrogen, and once the first atoms get to the detection site, I start seeing a rise in this curve. Okay, that's basically an intensity or an oxidation intensity, oxidation current that I measured here. Then, of course, at some point you have some kind of equilibrium, so you reach a steady state. Okay, that you reach here, and you can produce more hydrogen on the left-hand side, and then produce a second curve. Okay, so make more hydrogen past that sample. So you have those kind of transients. With those transients, I can apply different solutions. I can directly apply this using like numerical models, or I can apply it with some like analytical solutions, like very simplified solutions. So if you apply different solutions of each-second law to those curves, you can get the diffusivity, okay, in each of them. The main problem here is, okay, to apply fixed-second law, I need to assume some boundary conditions, okay, for my differential equation. But which boundary conditions are they? Like, do I assume a constant hydrogen concentration on this surface? Do I assume a constant hydrogen flux? And mix between them? Is hydrogen also like, once I produce it, like recombining and going back again to my solution? So all of those things needs to be considered only through an equation, okay? And that's where it comes one of the weaknesses of this technique, that you need to assume a boundary condition and then apply an equation to calculate the diffusivity, okay? Let's say how fast hydrogen moves in the material. Then started to think, and I said, okay, some other things that could be providing, let's say, scattering my permission resource, no, or less reliability. One of them could be like, okay, I have an electrochemical process, so I have a solution with a pH and a temperature. We know that even though I try to do everything the same all the time, we are not machines, so you have some, let's say, variability there. Then you can have surface effects, because when you do permeation, you produce hydrogen and you have a lot of bubbling on the surface where you are producing hydrogen. So that can reduce the effective area that you are permeating. You can have effects of the thickness. It's not the same doing permeation on a 20 micrometer thick membrane than doing it in a 3 millimeter thick membrane. Okay. So all those things are gonna, let's say, increase the scattering that I have between experiments. Finally, we have also this trapping phenomena that I told you before. That's maybe a bit harder to understand, but imagine a material that has a lot of defects, hydrogen traps. At the beginning, when I start the experiment, that material doesn't have any hydrogen. Okay, so before I start seeing something to rise, and even during the transient, all those effects are going to be trying to capture hydrogen while hydrogen is flowing to the other side. So that's going to affect my results. So that's what I call trapping effect. But those defects are more or less filled with hydrogen during the first transient. So after the first transient, in the second transient, those effects are minimized, because most of the traps are already filled with hydrogen. So that's what I did in this case, 2 permeation transients. So in the second transient, that trapping effect should be, let's say, negligible. So this is one technique, hydrogen permeation, and you can see here fitting of the curves with different boundary conditions. So you see, even though most of them provide amazing results, are coefficients of higher than 0.96, it's very difficult to really say, okay, with this boundary condition, you are getting closer to the results than with this other one. So you really, it's like a bit arbitrary. Like you say, okay, I will consider this, and I will provide a diffusivity based on just my decision. Okay. And then the second method, which is of course the one I'm supporting, it's based on thermal desorption. So basically, you charge your sample with hydrogen, but you don't measure any diffusivity there. You just fill it with hydrogen. Then you take your sample, you put it inside this main. That's a mass spec. It's ultra high vacuum mass spec. So it operates at pressure that are at the power of -9 millibars. So basically, the only thing you detect is hydrogen. You leave the sample inside, and you keep it at a constant temperature, the same as we did permeation. In this case, it's room temperature. And what you do is the sample initially is saturated with hydrogen, completely filled with hydrogen. So you leave it desorbed there in the TDS, and you record this desorption rate versus time. So in the end, you get a curve like this that you can fit also to second Fick's law, and you can obtain the diffusivity. Okay, the only thing you need to fit is the diffusivity. So we let's say adopted these 2 experimental approaches, permeation and desorption in the TDS, and we compared the results. So focus on this plot, or this figure. I'm not sure if it's called plot. On this figure, we have the methods that we used in the paper: permeation first transient, permeation second transient, and TDS, okay, isothermal TDS. So the desorption method. The diffusivity is here, black dots. So you see variation of diffusivity depending on the boundary conditions that we use in permeation and in TDS. And this is coefficient of variation of the more than 10 experiments that I performed using its technique. So let's look first, at the coefficient of variation. Okay? So what we can see is that in permeation, the coefficient of variation depends a lot on the boundary condition that I choose the sample to have. Okay? And at its minimum when I assume a constant concentration of hydrogen in the entry side, and in the second transient, where I don't have trapping effects. Okay? And then, if I compare the diffusivities, I have very unusual high diffusivities for this boundary condition and this boundary condition and this boundary condition, and very similar between this one and this one. Okay? So I consider here that, okay, to have some kind of reliability in permeation, I need to do more than one transient, so I need to remove trapping effects, and I need to assume, in this case, constant concentration of hydrogen in my entry side of the sample. And if I compare it with isothermal, I said, oh, I'm getting almost the same result. Also, you have to consider the orders of magnitudes that we are working with in diffusivity, so it's something at the power of -10. And so what we can see is, okay, with isothermal TDS, we obtain the same value as permeation, but the error was considerably lower. So it was below 5% in more than 10 measurements, while in permeation, it was the lowest we could obtain was around 8% here. And I had to assume things. In TDS, I know exactly my boundary conditions because I have hydrogen in the sample, and outside I have vacuum. So that's clear. So that was the main conclusion that we got here, that with this technique, that of course relies on a piece of equipment that's about 100,000 pounds. Sorry. So with this equipment, you can have way better results than if you just use permeation. That said, I think you can get it in AliExpress for less than 200 pounds. So I could do the experiment at home, basically. But that's my takeaway. Of course, I'm going to be using TDS. But we need to be very careful if we use electropermeation to be sure of the boundary conditions that we are using. Now, that's something that people are usually careless when they calculate hydrogen diffusivities in papers. So that was our takeaway for this paper. And then some applications of this isothermal TDS technique was, for example, we managed to apply it to pure iron at different temperatures, which is usually very hard because pure iron hydrogen diffuses really, really fast. Like you charge it, and in less than 1 hour, probably you don't have any hydrogen in pure iron. So we were able to measure diffusivity there at different temperatures, and also Claudia is familiar with this. We apply this isothermal desorption also at very high temperatures, even to 400 degrees, because it's another advantage of the TDS, that you can really heat your sample as high as you want. Unlike permeation, that you are limited by boiling of the solution, because in permeation, okay, you can do the test at higher temperature, but above 70 degrees, everything becomes very tricky. So we managed to calculate the diffusivity of different Inconel grades at a very wide range of temperatures, which is very useful to know which is the diffusivity in real applications. Okay, for example, imagine you have let's say, blade of a turbine that's going to work at 500 degrees. Then with this technique, you can know which is the diffusivity of hydrogen at that temperature. And this is a second project that we were working on, I think we finished last year, and we published this paper. It's also a bit of experimental, comparison of experimental procedures. But I think it's pretty interesting. So in this case, it's a completely different area of research inside hydrogen embrittlement, because it's studying fatigue with hydrogen. Okay, in this case, in steels. So we are really interested in knowing how hydrogen affects the fatigue behavior or the crack growth behavior when we have fatigue loads in different structures, because it remains like a, let's say, relevant fracture mode in real structures and real applications. And actually, hydrogen is able to drastically reduce the fracture toughness of these kind of steels, like, let's say, chrome molybdenum, like steels. So it's able to reduce it drastically. So we really need to study this kind of loading. And actually, it's very relevant nowadays for the current and the future hydrogen pipelines that right now are manufactured in pipeline steels, which are called pipeline steels, but that we don't know if in the future we'll need like to rely on more advanced steels like these chromo-molybdenum steels. So we really need to address the topic of hydrogen like assisted fatigue when we have high hydrogen pressures, when we have welds, and when we have this kind of material. So this was the aim of this paper. And we have two ways of characterizing fatigue in metals. So if you think about what we did before for the TDS, we can charge our sample. So this is a sample that we use to test fatigue crack growth. So you can charge it and then test it mechanically, okay, and then do fatigue in air. So you fill the sample with hydrogen and then you do fatigue in air. Or you can do fatigue in a hydrogen environment. That's more similar to what we have in a real case scenario, right? Like we have a pipe that's carrying hydrogen, and then you have fatigue loads. And so we wanted to compare the results from both techniques at the same time that we were characterizing the fatigue, let's say, behavior of these steel welds. So we did it in, but we actually don't need to go into detail, but we did it in a chromo-molybdenum steel. That right now it's a steel that's used to manufacture typically vessels and bolts and that kind of like big bolts. Don't think about the tiny bolt, but like massive bolts and vessels for industrial applications. So it's like let's say a steel that we could perfectly use in 20 years to carry hydrogen at low pressure. Okay, so we use this steel, and specifically we use welds of this steel, okay? Because the welds are usually the most sensitive area of a structure, okay? Because it's where we join different parts, and it's usually where we have more defects, where we have more interfaces, and where the material is inherently more brittle. Okay, so we have more defects, and hydrogen loves defects. So what we did was to do fracture crack growth test. I don't know if you are familiar with fracture in general or with fracture testing or fatigue testing, but basically what we do is, just to be more simple, if we have this sample, what we do is apply a load, okay, that's a cyclic load, so it follows like a cement curve. So we apply that load, and basically we are pulling the sample like this, okay? So the crack that's here, if we pull the sample, just pull and release, the crack is gonna grow, okay? And when you pull with a certain load, you create like a stress intensity factor there, okay? So what we measure in fatigue is the millimeters per cycle that the crack is growing versus this stress intensity factor range, okay? So this is the behavior of one of my materials, let's say, because I compare two materials, one in the base metal and the other in the weld. Okay, so this is the behavior of my base metal with no hydrogen. Okay, and if we go to the CM and check the fracture surface, we see that all these striation marks are indicative of ductile behavior. So okay, no problem here. We tested then the weld. Okay, so remember this is far from the weld and this is the weld. We tested the weld. We had a similar behavior than the let's say steel far from the weld, and we also see these striation marks. Okay, so that's the behavior. So we did the same then for hydrogen. We can see that we have a completely different behavior here. So what happens is that my graph growth rates have increased a lot, basically at the beginning of the test, and they tend to overlap the rest of the curve, so the, let's say, non-hydrogen part of the curve for higher values of delta K. And it's very interesting to see the effect of the frequency. So when I do fatigue, I can choose the frequency, okay, with some pulling. And what we see is that if we go to high frequencies, like closer to the ones of the samples that didn't contain any hydrogen, the behavior is exactly the same, but I have to reduce the frequency by a couple of orders of magnitude to really see an effect of hydrogen there. Okay, and I did the same with the weld, or with the metal next to the weld, and I observed the same behavior. And it's interesting that when I went to the SCM and checked these two samples, I observed that these striation marks had disappeared. So I couldn't see any sign of, let's say, this ductile crack growth, even though here we still see some ductility in the material far from the weld. But in the material close to the weld, you can even see that we have this intergranular cracks. Okay? So you see, the main takeaway from this slide is, okay, when we have hydrogen and we test at low frequencies, we do really see an effect. Okay, so the material is becoming more brittle, and then the crack is growing much faster. Okay, when we do fatigue. And then what we did was the same, but we tested in a hydrogen environment. Okay, remember that the previous was for a sample that I charge with hydrogen and then I test. So now what I said is, okay, I'm going to put my sample in a hydrogen environment, like I did here, and I'm going to test at the same time. And I'm going to apply 35 megapascals of external hydrogen pressure. And what I got was, okay, this is my reference curves, the same as before, no hydrogen, and then boom, what happened here? Completely different, right? But we'll talk about the difference later. So this is what happens in the material far from the welds at a high frequency. So that's interesting that I didn't have this kind of frequency effect here. At 35 megapascals of hydrogen. So now we don't see that flat trend and that trend to overlap my let's say hydrogen-free behavior, but I see this parallel, let's say, crack growth to my master curves. And if I check here, I also don't see any like striation mark. So remember, because that's done in hydrogen. And I said, okay, let me see if there is any effect of fatigue. So I reduced the frequency even more to have the same frequency as we had in the other experiments, and the curves were overlapping. So I said, okay, it's weird, interesting. In this kind of experimental procedure, there is no effect of frequency. And of course, again, I observed like no, let's say, ductile behavior during propagation. So then what I did was, okay, the same in the weld, and I obtained exactly the same trend. So no difference in the curves between different frequencies. And in this case, as it happened before, we have some intergranular cracks and even more brittle behavior than far from the weld. And then we are going to compare, but you can already see that okay, maybe not at the beginning, but after some crack growth, the crack growth rate in my zone close to the weld is considerably higher than in the one far from the weld. So I said, okay, I need to directly compare the results on the same plot. We have the results in air, no hydrogen, then we put hydrogen and then we test, and then we test inside of hydrogen. So on inside of a hydrogen chamber. And we see the behavior is completely different. And it's interesting, right? Like, why do we have this different behavior? So here, actually, we have, this is unusual. When you see this kind of propagation, like this kind of curve, you usually see a like Paris propagation region that's more or less linear. And here we have a flat, where the, let's say, crack growth is constant. And it resembles more like a stress corrosion cracking process. Okay? So we said, okay, let's compare it with the literature. Let's drop, even though we couldn't find a paper where they compared both methods, we compared two skills, like this, like two, let's say, research papers where we tested the same skill with the two different approaches. So this is for a hydrogen atmosphere, okay, in this case at 21 megapascals, and then some other people in the same material but with pre-charged samples, okay, with samples that were tested in air after hydrogen charging. And they observed also the same exact behavior as we did, okay? But they didn't notice these differences because they were different rates, okay? Okay, so we said why is this happening? So to understand why, like I couldn't find an explanation until we did some simulations. Okay, so basically what we simulated, we wanted to know which is the amount of hydrogen that you have in the front of the crack when you are doing fatigue. Okay, so basically how much hydrogen is like being involved in this fracture process or in the cracking process. Okay, between the two methods. So what we see is this is the hydrogen content at 1 micron from the crack tip. And this is the time of experiment which really like didn't matter for us. We just wanted to know what was happening. And see that we introduced like a loading, like a cyclic load, okay? For the two different conditions. So if we have a look to the samples that were tested in a hydrogen atmosphere, the hydrogen content in the crack tip was pretty constant along all the experiment. While the samples that were pre-charged first and then tested in air had this behavior. So we saw that hydrogen was okay, very let's say big at the beginning, but pretty like soon after we started the experiment, the hydrogen concentration dropped below our hydrogen concentration in the let's say samples tested in the hydrogen gas atmosphere. So okay, this can actually explain, and I'm going to go to the next slide, why we have this flat region here. And why? Okay, because we have the sample that we are testing like in a hydrogen atmosphere, and the hydrogen that is outside is, let's say, being uptake all the time in the crack tip, like along the experiment. Okay, so hydrogen uptake is continuous. So I have always the same flat trend, like it's the red, okay? But when I pre-charge and then I test in hydrogen, I have, okay, the maximum hydrogen concentration at the beginning of the test, but as soon as I start cracking the sample, you have a lot of hydrogen that's, okay, going to your crack tip, but also most of it that's trying to leave the sample through the crack and through the sides of the sample. So you are slowly losing hydrogen concentration in your crack tip. And that's why we have that flat behavior, and eventually, after some hours, then you overlap the hydrogen-free behavior because you no longer have hydrogen around to bring to the crack tip, okay? While in the other case, you are feeding the crack tip with hydrogen all the time because you have infinite source of hydrogen in the environment, okay? And that can also explain the frequency behavior. And it's very easy, it's the same explanation actually. When you have hydrogen outside that you can feed infinitely to your, let's say, crack front, it doesn't matter how fast you load and unload the sample, okay? Because hydrogen doesn't need to flow slowly to your crack tip, like happens here, okay? If here you don't give hydrogen enough time, the hydrogen that you have in the surroundings of your crack to diffuse to your crack, and your crack is growing so fast that hydrogen cannot catch up, then you don't have embrittlement. So we find out that those were the reasons why we were having that difference of behavior between both experimental methods. And then the last thing we wanted to explain was why the area close to the well were behaving so badly compared to the area far from the well. We discovered that, okay, the zone close to the well had a grain size that was massive, and actually you can see the grains that are very big, while here the grain was much finer. So what happens, and they both had the same hydrogen concentrations, and they were tested in the same conditions. So what happens if you have the same hydrogen in a grain size that's much smaller? That, let's say, the density of hydrogen in those internal interfaces is going to be much lower because you have a lot of internal interfaces. While if you have very, let's say, big grains, so you have less internal interfaces, the amount of hydrogen that you're going to have in those interfaces is going to be greater. Okay? So it's basically density of interfaces. So we had less density of interfaces there, so hydrogen was very prone to embrittle and make cracks grow through those internal interfaces. While here it was a bit different. We saw that the cracks could grow like transgranular and not intergranular. Okay. So basically, be careful with wells, because when there is hydrogen around, they become even more brittle than they are. Okay. So that's basically the main takeaway. And I think I'm running out of time, but I would like to show you the last, like, just very quickly, the last project that we are working on, and this is actually like my baby. Like, I'm cooking it slow because I want to publish it in Nature. And so we are investigating the effects of that hydrogen has on plasticity, and we are doing it through, let's say, a different approach. And I'm gonna just try to show you why. So what we see usually, it's the same curve as I showed before. Like, hydrogen has an effect on my stress strain behavior. Okay, so you can really see that's making it more brittle. And if I go to an SEM like fracture surface, I actually can see that when we have hydrogen, like microscopically, we can see this brittle behavior, right? Like characterized by intergranular fracture. And so if we see a brittle fracture there, then why do we see that we have still accumulated plasticity here? Okay, that's somehow like a bit contradictory, and we cannot explain it with just one of the mechanisms that I explained before. So we really want to understand how does hydrogen interacts with plasticity. Because it's really important to develop the models that then will be able to predict how a bigger structure is going to behave in, let's say, in the middle of a hydrogen-rich environment. Okay. Typically, this kind of research, like more fundamental research where we want to study hydrogen plasticity interactions, has been conducted using, like from a nanoscale, let's say, using techniques that allows you to see a single or a bunch of dislocations, or like an indentation that you also target, like, let's say, micrometers of your material, right? But then, and we can draw some conclusions from those studies regarding hydrogen and plasticity interactions. But the main problem is that those approaches are very local, and they depend a lot on the place of the microstructure where you study the phenomenon. Okay, so we wanted to overcome a bit those limitations and adopt a complementary approach that allow us to study the effect of hydrogen over a large scale. So let's say a sample size scale, and also isolate the fracture process to the deformation process. So don't really, because if you also try to study something here fracture is taking place. So it's very hard to isolate what's going on only during deformation. So we decided to adopt an approach that's based on studying the texture evolution of a material when you deform with hydrogen and with a hydrogen inside. I'm not sure how familiar you are with this, but basically texture is like, if a material has texture, it means that it has, their grains have preferential orientations, okay? And this development of texture or of preferential orientations in a grain is related to, or it's actually directly related to the active deformation process that's taking place in the material. So basically the slip systems that are active or the slip systems that are not. So really studying how hydrogen affects texture evolution can give you information on how hydrogen affects plasticity. So what we could say is like, okay, if we observe faster texture evolutions in the samples that have hydrogen, then it means that hydrogen is enhancing plasticity. Okay, it's fostering dislocation motion. And basically sliding of dislocations of the slip systems. Then if we saw a slow texture evolution, then hydrogen is like pinning my microstructure and hindering deformation. Okay, so what we did was to charge a bunch of samples with hydrogen, Okay, so we tried to introduce as much hydrogen as we could. In this case, around 8 ppm, but the number is, let's say, not relevant. On pure nickel, okay, with a random texture. So we don't see preferential orientation of grains here. So we charged the samples with hydrogen and we did core rolling, okay, because we wanted to introduce as much deformation as we could without breaking the sample. And with tensile test, we can only go to maybe 10%, 15% of deformation, okay, before fracture. So we deformed a lot the material up to equivalent plastic strain of 1.5. That's compared to tensile that you can maybe get 0.1, it's a lot. And we measure the texture, okay, using different methods. So we use EBSD and then we use XRD. I'm sorry, I'm running out of time, so I cannot really explain how to do it, like how to measure texture through each of the methods, but I'll show you some of the results. So this is an example of texture measurement through EBSD. Okay, so the more similar colors you see in a picture, it means the sample is more texturized. Okay, so we studied, we did like EBSD scans for all the deformations that we studied with and without hydrogen, but we realized that it was going to be very difficult to get like some really like statistically robust conclusion from here, because we had, as we deformed the sample, we have very large grains, very like elongated grains, and we cannot really capture the behavior of a lot of grains. And for EBSD to be really like representative, we need to analyze at least 10,000 grains, for example. We said, okay, it seems we see something, but we cannot really claim something. So we went to XRD measurements, where you study more like you measure the bulk of the material, and we obtain the Paul figures that are other, let's say, measure of the texture that I'm going to explain. And these Paul figures, you can just, let's say, do some kind of average between them and get a number that's called texture index that gives you an overall strength of that texture, of how like the material, how strong the material is texturized. Okay. So if you look at the plot, and that's the plot that's taken us to nature, we can see the evolution of the texture index versus the plastic strain. Okay, so it's how the material is texturized with different plastic strains. If we check, the non-hydrogen points are the blacks, and the hydrogen points are the reds. So those are a bunch of samples that were charged with hydrogen and core rolled to that plastic strain levels. So what do you see there? Like what we can see is basically that the behavior of the samples that had hydrogen and the hydrogen-free samples was pretty much the same up to plastic strains of around 0.5. And that from that point, it seems to be an effect of hydrogen on texture evolution, which would imply that there is an effect of hydrogen on plasticity. And in this case, the texture evolved faster in the hydrogen charged samples, so that means that in this case, hydrogen is enhancing dislocation evolution, okay, in this sense. However, even though we have around 200 samples in this figure, so it's a lot, so around, 200 measurements in this figure, not 200 samples, we still want to have like more, let's say, robust results, so we can really do a statement here and say, okay, hydrogen is doing this on plasticity. So my next steps, and actually after this, I'm running to the material science lab to do some of the measurements. I'm going to repeat this for a different hydrogen concentration. So I want to have here another curve for hydrogen, but with a much higher hydrogen concentration to confirm these results. And I want to do some simulations to see which is the sleep behavior and change parameters, like to get some information on the sleep systems that are active or could be active when we have hydrogen or we have not. And in general, that's all. These are some concluding remarks of what I said today. So basically, we need to be aware that mechanical components can fail due to hydrogen in different industrial systems, mainly in hydrogen pressure storage, in aircraft components, and in high-strength alloys. Then that an accurate measurement of the diffusivity, that's it, the speed of hydrogen inside the metal, it's very important to design safely these structures or these components. Then that we need to be careful when we choose the method to assess the mechanical behavior of the structure in presence of hydrogen. Like we need to really use in situ tests, in situ experiments. That there is still a lot of controversy on the underlying hydrogen embrittlement mechanisms. So we need to publish more papers and do more research on that. And then that understanding all these mechanisms, and even more if it's in new additively manufactured alloys, it's probably the first step towards the mitigation of the phenomenon. That's it. I hope you have enjoyed, and yeah, thank you for coming.